I have the pleasure to present the Associate Professor at the School of Civil Engineering, Haris Mouzakis, who was as well responsible as a deputy chief to the site works. So, Professor Mouzakis, you are having the floor.
Thank you very much, Professor Moropoulou. And I'm going to present you what we did during the restoration project of the Holy Edicula. The first thing were the safety measures at the work site. The aim of the implemented safety measures was the protection of both the pilgrims and the personnel. That's why the first thing we did was to change the path that pilgrims had to go along it to come inside the edicule and then to get out of it and to get out of the temple. That's with the magenta color. You can see how the pilgrims have to walk in order to enter in the edicule, and with the blue lines, how they had to get out of the church. With the red line, you can see the work site that was closed during all the works we did up to the end of the project. Then the personnel was trained to perform the required work by using this scaffolding that was properly designed and constructed for the case we had to take out, our case where we had to take out the cladding of the edicule. The entrance of the edicule was covered by this steel cage, and this structure was designed to be very stiff in the case that any material from the work site was falling. This steel structure was strong enough to avoid any accident. The second measures we took were about the protection of the monument. You know that there was existing the British steel frame since 1947, and these steel frames were placed at the north and south facade of the edicule. We did an analysis of this steel frame, and we found that it was inadequate for the restoration of the monument. That's why, after taking into consideration the results of the structural analysis, we decided to strengthen the cantilevers, the cantilever beams, with this diagonal that was at the base fixed on the ground. These beams were HEB 200 beams, as shown in this picture. At the east and west facade, there weren't any steel beams. That's why we placed these steel new steel frame, where the new beams we installed, they were working as cantilever founded on the rock in the west and east facade of the Edicula. You can see here the new supporting frame of the east facade. In the Edicula, as you enter it, on your left and right hand, there are two staircases that if you take these staircases, you can go on the roof of the Edicula. Then we had to support this area, as the thickness of the masonry was not appropriate to remain without any special measures. That's why, to avoid the collapse of the worst part of the monument due to vertical loading or an earthquake, we decided to erect this supporting truss with bars inside the staircases. In the anion dome of the Edicula, we install stainless steel supporting frame that we decided to remain. That's why it is stainless steel, and even now it's a remaining scaffolding inside the anion dome. At the end of the project, where we had to cut all these steel bars all around the Edicula, we had to use fire cutting without oxygen, but to use to cut it with a special system. We constructed a timber parapet in order to avoid damage on the Edicula that already had been restored. When we took out some cladding of the facade, of the north facade, it was clear that the quality of the load-bearing masonry of the Edicula, it was not of an appropriate good condition. It was a masonry that the mortar was damaged, that were from the findings that the first study Professor Moropoulou performed, and they found that the quality of the mortars was very bad. And also the quality of the stone masonry was of low quality. That was a type of masonry, stone masonry, they called kakuli, and it was a very low quality. And we decided to reconstruct the masonry. But as you can see here, in order to start the reconstruction of the masonry, we were not able to take out all the stones that were in one facade up to the height, we took out the facade, but we had to support this masonry, and at that time we found that the best way to do this was to put a cantilever beam, a steel beam. You can see these beams, HCA 100 beams that were placed horizontally. We put a steel tube under this in one place, and on the other part, this beam was fixed on the supporting steel structure that was existing in the edicule, as it was strengthened with HCB 200 beams, as I mentioned before. For this, if you analyze the forces here, you will find that there is a vertical force from the weight of the masonry, and then you have a moment that can be analyzed to a compression strength here and a tension strength there. And this moment is there is an equilibrium with these vertical forces we had from the existing masonry. That was the way we managed to take out the existing masonry, and then we'll started the reconstruction of the masonry with new blocks. The blocks were 400 by 400 by 20 millimeters, and we used a mortar of Master Mako S285 ticks with a strength of about 15 megapascal compression strength. And we started and we reconstructed like in this way. You can see here like a trapezoidal shape of when we constructed it, we gave it to the masonry. Then we took out these two beams and we continue by placing new stone masonry, and then we took out this and that beams out, and we continue all around the areas we had decided that this reconstruction has to be done. This job was done at the height, in some cases, up to the height of 2 meters. The initial, the height where we put these horizontal beams was of about 120 meters. You have to be, in the case you have such a type of structure to keep it in situ. The thing also you can do is to put some diagonal beams here and there and other horizontal beams and try to support this structure, but this is more dangerous as you are not able to put some beams under the masonry. We were very lucky that we had this steel structure, and we were able to place and install this cantilever beam. Then we have to explain some restrictions we had on the applied interventions. You can see here that as when we took out the cladding, we had to keep the arches to support all these arches. we decided to construct this timber supports that again we support them from the steel bars of the steel structure that was all around the edicule. During the time that the cladding was absent from the monument, these beams, timber beams, were very helpful in order, even if we had an earthquake, these arches were supported. During one of the measures we had to take into account was to use injection of mortars in the edicule. And for that reason, we had to be careful with the tomb of Jesus. That's the reason why it was decided to open the tomb. When we started opening the tomb, the first thing we found was that this marble plate that was placed horizontally on the tomb by the architect who had constructed that plate and designed that plate was fixed in the wall. Therefore, it was not easy for us at that time to find exactly where were the points where this slab was fixed. We didn't know exactly the points. That's why we'll start moving a little bit the slab in around a vertical axis, and we found the poles of movement. And we found finally that there were two steel rebars that were not allowing us to take out the plate. Another restriction we have when we were trying to open the tomb was this line you can see here on this plate, this red line here. The slab was cut in pieces. If somebody will try to open the tomb without, at these points, there were the two rebars where the plate was fixed. If you try to open the tomb, then the thing that will happen is that at this area here, which is the softer area, at this point, the marble will be broken, especially if you have a bending with a moment at the vertical plane like this. Therefore, that's why we place these timber beams on the top of the marbles to increase the strength of the plates. But again, it was very dangerous to support the beam and try to take it out by changing the level of the beam. Due to the weight of the beam, the slab was going to be broken at this area. You can see here that at this area and another area there, the slab was broken in the past. That means that that in past somebody tried to open the plate, and they didn't manage to do it. They were afraid that they are going to break this plate and somebody will understand who did it. That's why they keep it there with these areas to remain broken without any restoration of these areas. And then what we decided? We decided to put a steel structure under this plate, and as you open, have in mind, as you open a drawer, to move the plate by leaving it at its original position and move it like a drawer on the steel structure. You have to know that when you are in such areas, when you are at the work site, everything will not go very well as you have designed the things. And what happened? We were waiting that at 4 o'clock, a mechanical engineer, technician, was going to come and weld the steel structure. And you have to know that he never appeared at the work site. There we decided to construct a timber structure, and that's why we place under a timber. You can see that inside here in the area there are some timber beams. That's what we had easy in the work site, and we constructed this timber frame on which we placed the marble plate without trying to change its vertical position. And then we open the dome, and there were a lot of people, especially from the three communities that were waiting to come inside one by one and see the tomb of Christ. What I have also to tell you is that we were at a pressure from, maybe Professor Moropoulou could explain better for these things, but we were in a pressure as we have to be very careful that nobody will come and place a mechanism or something and have an explosion or something unexpected in the work site. That's why we had to be very careful, and everything all around the edicule was very well examined many times, as well as we had the protection of the police of the Israel police, and there were finally nothing bad happened, and we managed to finish our job. Another problem we had to solve was that in the inner part of the edicule there were interior frescoes, and during the grouting we had to retain these interior frescoes in order to avoid delamination of them from the mortars that were placed on the edicule. Another goal of our job was the repositioning of sluggish columns. The sluggish columns are these columns between the facade stones that are of red color, if you have an icon of this monument. And these in the past were out of plane. You can see here with the blue color the position of the of these sluggish columns as it was recorded from the British. You can see here from the British report, from the report written by Freeman, that was written at 1947. And with the red lines, you can see the position of the columns of these sluggish columns as they are nowadays after the restoration. You can see here that we used many, these red are actuators that we used, mechanical actuators, like the ones you have in your car, that you can change the tire if you have a problem. And we managed to control the displacement of these marble pieces in order to be exactly in the vertical position along both directions. And that's how we manage, by using these actuators. That actuators were fixed on the steel structure again. You can see that this steel structure was for us the best we could have in the work site. We were very lucky that we had all these steel structures, even the new structures we constructed there. Otherwise, it was not easy for us to apply these forces and impose these displacements to manage to put these columns at their initial vertical position. These are 5 columns on the north facade, 5 on the east facade, and then we had also to replace the columns on the east facade as well as at the west facade. I had to mention that this is a small chapel of Copt church, and we had also to take this out and take out these marbles at this west facade. We managed to do all these things, and after this repositioning of the columns, we had to replace all the marble facades that they were moved on the first floor of the rotunda, where we had the laboratory that they repair and clean all these this stone facade, and then we had to replace it. But how we are going to place these facades, this stone facade, and keep it in contact with the existing masonry? In that case, we had to use titanium bars, as Dr. Mouzakis mentioned before. But what questions we had to solve before doing this job. The first thing was, what is the length of the titanium bars that has to be placed in the masonry, stone masonry, in order to have, during the pull-out test, to have yield of the stress of the titanium bar, and not to have damage of the mortar where the titanium bar will be placed inside the holes we open. That's why we drilled a hole. We used master Mako, but not it's in the commercial condition. We had to take out all the fibers that are inside the master Mako, and also we had to press, to find a way to press the mortar inside the drilled hole. Then we had to place the rebar in the hole, and we had to pull out this titanium bar and see that the bar is yielding and not, or is cutted or is damaged, and not to have slipping of the titanium bar in the hole. That's why we constructed this steel structure, where we used a special hydraulic actuator. We install the bars, some bars at the initial condition, without having there the marbles, and we perform the pull-out test, and we found that really we did many experiments, and we found that really, if you use a depth of 400 millimeters, it's enough to have yielding of the material. And we tested 1 week later than the injection of the mortar, although we had, and we got these good results, although we had to wait even more days. But what we wanted also is to have a coefficient of safety, and that's why we did this extraction within 8 days. Then the second thing was how these titanium bars will be touched and will be keep the marble, not the marble, the stone cladding. Therefore, what we did, we constructed, the first thing was to be able to know that we are able to bend the titanium bar without damage it. If you try to find something in the references, you will never find it, as the only thing you can find are what we can do for steel rebars. And that's the reason why we started with the diameter of cylinders that can be used for the rebar as it is used for reinforced concrete. We did this analysis, these tests, and we found that it's enough to use exactly for the diameter of the rebar to use the appropriate cylinder, as it is the similar cylinder like it was a bar of stainless steel or a bar of steel that is used as reinforcement. And then we asked the technician, of the marble technician, to construct here a curve similar or very close to the curve that the cylinder gives. And if you look at this, you can see that it's a similar situation as we have the bending we are doing for the bending of the steel rebars in concrete. Then we performed the pull-out test by pulling this rebar, and we found that at the yielding point, before reaching the yielding of the rebar, sliding started, and then the marble was not damaged, the stone was not damaged at all at this area. That was good for us, as we didn't want it to damage the marble and broke the marble in the case of a strong earthquake. Another thing we had to take also into consideration, it was that behind the marble, the stone cladding, we had to cast in situ Master Mako S285 mortar, and for that case, what happened? When you fill this area with this material, you can see here, when you fill it up to this level, then you have to put the next level of the stone masonry, and then to cast again this Master Mako mortar. That means, in that case, if you work like this, what are you going to have? You are going to have here, at this level, full joints between the two casted mortar, and also it's not a very good thing, as between here you can have some pieces of sand, and these two pieces are not going to be well joined. That's why we decided to put a very low diameter rebar of titanium, and have horizontal and vertical reinforcement of titanium bars between the facade cladding and the masonry on which the cladding was going to be supported. Another problem we had to solve was how these anchors were going to be placed at the slabs of slaggy stone with the red color, as I mentioned before, and we decided to drill holes. That was easy, as when you have this thing, this facade, you drill a hole here. We placed the titanium bar. We placed here a special titanium circular plate. Then we fix it there. But at the end, what we did were to have many holes on the edicule. Look at here, at this. With this magenta dots, you can see the areas where all these bars all around the facades were placed. These are the anchor positions on the cladding surface of Sluggish stone. You can see here that the interventions were not only at the area where we replaced the, we took out and replaced the stone masonry, the Mizi facade, but was up to upper zones, as at these areas only ejections of mortar were performed, and we didn't place any material like master and mako or rebars as we did in the other areas. That's why we placed 2 bars here for each piece in order to keep it in a good position for a future earthquake. Another problem we had to solve was that all these on the top at this area, at many locations, this stone Mizi beams, no Mizi, I think Sluggish stones were dispositioned from the vertical line, and we had to replace them. When we tried to replace, there were some problem with the changed length of the horizontal beams of these beams here. And finally, we managed to reposition all the material at its position, not exactly at a vertical position at all points. There are 2-3 points that are not completely in the vertical position, but it's not easy by the eye to find it. Only if you place some special instrument there, you can find that it's not exactly in the vertical position. It took us a lot of time, all these measures to be applied. I have also to show you a table here where you can see some results of the pull-out test that we had a stiffness that is Newton millimeters, like to have springs, if this were used as springs in the finite element model, this anchoring rebars. You can find, we found the stiff that has to be used, and the maximum load that each bar can take. You can see that we had 10 kilonewton for the bars that were placed on the Mizi stones, and 20 that were placed on the Sluggish plates. Then one of the other things we had, but it's the only thing was that we had to check the structural integrity of this anion dome on the top. We did an analysis with a finite element model, and we found that the best thing we had to do was to put inside this stainless steel supporting frame. On the top, there was a vertical beam, and all these all-around beams are nailed on this vertical beam. This threaded here bar is used to support this vertical beam. In the case that we are going to have a strong earthquake, this vertical thing will remain at its position, and we are not going to have a problem as this steel bar is still support gets sent the forces on the marble or on the top of the edicule. Finally, what we have done is that we know how much are the forces that all these titanium bars we placed can undertake during a force that is, as this cladding is acceleration and not drift sensitive, what is needed is to know the acceleration of the earthquake. When we started the first, with Professor Moropoulou, the first measurements of the Church of Resurrection and the Holy Edicule, at the Holy Edicule, we measured the natural frequencies of the edicule. Knowing the natural frequencies and the response spectrum of a future earthquake, we'll know the acceleration of that will take place on the edicule. Have in mind that you have an acceleration of about the maximum 1.5 g. Then, if you have a mass of the facade of each block, which is 7 kilonewton, it's 7 kilonewton or more, it's 0.7 megagrams or 1 megagram, and multiply by the acceleration, you are going to have a force of 15 kilonewton. Therefore, you can see that these values, for example, at the beams, are enough, nothing will happen. The same will happen with on the Mizzi marbles, as we have more than 2 rebars that are placed for each masonry, of each block of masonry. And that's enough, and we are knowing that the edicule is safe. But in the case that an earthquake will happen and the dynamic characteristics of the earthquake will be different than the given from the seismic hazard analysis of the area of Jerusalem, then we had in mind that is needed to install a simple system of triaxial accelerometers on the edicule. We placed an accelerometer on the ground floor, on the ground, on the rock, another accelerometer on the top of the edicule, and another there in order to record rotational also vibrations due to the reason that it's not a completely symmetric structure. And by knowing these accelerations and the masses of each block, we'll know how large were the forces that were applied on the steel, on the titanium rebars. That's what I had prepared to explain you. And if you have any questions, I will be very happy to give you some answers to your questions. We have about 10 minutes. It was also, there was a fire protection, there was a system, a security system all around the fence of the work site. At the very beginning, when we started taking out the stones from the existing, from the edicule, at that time pilgrims were getting over the fence, and they wanted to take some stones and marbles of this. And have in mind that 5 years later, less than 3-4 months, I visited a monastery, and they told me, look at here, do you recognize this? And what was this? It was a piece that when we drilled the holes of the sluggish marbles, they took these things and they sent it to various monasteries in Greece. Therefore, you have to be very careful, and all these things were placed in a special area, safe area, to remain there. It's more than 2-3 years that I have not visited this area. I hope that all these stones remain there, and they are not spread all over the world. It's on them, of course, to decide, but we can say that it's not very good to make people to believe that a piece of stone is something that even they are religious people is significant for them.
Professor Mouzakis, can I make a question?
Yes, please.
From your experience from the Holy Edicule, do you believe this was more of an engineering challenge or more of a scientific challenge, or both? I mean, from what you presented to us.
Look, as a professor of the university, I have to tell you it was of an interdisciplinary need of have, for example, surveying. We started with surveying. We did analysis with finite element. We did measurements of natural frequencies. We did analysis of mortars. We did analysis of stones, of the strength of stones and the quality of stones. Then we used new stones. We had to be sure that this stone is of the same quality with the existing one. We had to clear the facades with special materials. You can see that the final goal was, of course, there was a need of an interdisciplinary team. But the restoration of the structural part, of course, it's I think that civil engineers have to solve.
Thank you. Thank you.
Thank you, Professor Mouzakis, for
You are
the
welcome.
very in-depth and in detail presentation.
It could be more in depth, but
I was very glad to attend it because it gave me the pleasure to see that you integrated in a written form all what you have produced on site. And of course, you were ahead of time, so you had not any spare of time to write down. However, it's great. Thank you very much.
thank you.
Is
Have a
there
nice
any other
afternoon.
question? Okay. Thank you very much. Good evening.
Good afternoon.